Hello, everyone. Welcome to this week's French seminar. Today we have three speakers. Our first speaker is Jin Song. Jin Song is the PhD student of Professor Zhenya Zhang. Zhenya received his PhD degree in 2022 in applied mathematics from the Dalian University of Technology in China. Then he joined the University of British Columbia as a PIMS postdoc from 2002 to 2003. From 2003 to the present, he has worked at the Academy of Mathematics and Systems Science at the Chinese Academy of Science and gradually became an assistant professor. And in 2007, he became an associate professor and then a full professor in 2012. His research interests include mathematical physics, solitons and integrable systems, Rolle waves, PT symmetry, Riemann-Hilbert problem and method, fractional nonlinear wave models, symbolic numerical computation, and scientific machine learning for PDs. Jin Song and Zhenya, thank you so much for your time today. And with this short introduction, you can begin whenever you're ready.
Okay. Thank you for the introduction. So, hello everyone. I'm Jin Song from Academy of Mathematics and System Science. Thanks, Professor Condex, for giving me a chance to have a talk. I'm so excited because this is my first time to talk in English. Okay, so today I will talk about a new structure about pins we call AttnPINNs, which is under the self-attention mechanism for PDs. It is designed to mainly simulate dynamical system with multi-scale high frequency or chaotic behaviors. This work is joined with my supervisor, GNN professor. Okay, firstly, I'm going to talk something about scientific machine learning. I think combining physical knowledge with machine learning is an important idea to achieve scientific machine learning. It's a core component of artificial intelligence and computational technology that can be treated with scientific data. The scientific learning basics research group identified 6 priority research directions as shown in the figure on domain-aware, interpretable, and robots. Also, this figure outlines a strategy to address the capability research challenges on data-intensive machine learning, enhanced modeling and simulation, and intelligence automation and design support. Okay, since I focus on the numerical results of complex linear waves and by some numerical methods such as imaginary time illusion method, Newton conjugate gradient method, and spectral method. So in my perspective, numerical method is basic on physical models and is robust and interpretable, but it may be lack flexibility and is large scale limitation. In contrast, machine learning method is mostly data-driven and hence generalization, where it has poor interpretability. So, combining physical information and machine learning will be a new paradigm for scientific machine learning. It was known as physics-informed machine learning. Okay, then I'm going to talk in this outline. Firstly, I will give an introduction about pins and some improvements. Also, the main technology self-attention mechanism. Then I will introduce my method, the framework of AttnPINNs, and the convergence analysis. In the part 3, I will give some numerical examples. Finally, some discussions and the summary will be given. Okay, I think the most familiar with pins, so I will give a quick introduction. Focus on this PDs, we can design a neural network to approximate the solution U such that it satisfies the equation and the initial boundary condition. Well, pins take the PD residue and the loss function, and by minimizing the LR set and the LB set such that the output of the neural network automatically satisfies the equation. Of course, here we use the general fully connected network compared with the traditional numerical methods. Machine learning method is match-free and automatic diffusion. So in the work of high dimension and complex domain, it can be much easier to achieve. Focusing on different challenges, a series of extensions to the AttnPINNs have been proposed, which mainly include but are not limited to several categories. Modify the loss function. For example, one introduces the new tangent kernel into the weight to accelerate convergence. Besides, there are some categories about adaptive sampling and domain composition and advanced network architecture. We will not introduce them here. And despite many improvements, there are still problems on pins. AttnPINNs may be limited when dealing with some problems. For example, the convection equation is treated as a failure model in pins, although it is a simple linear model. Here beta is the convection coefficient. The pins is unable to achieve the good solution for small value of convection coefficient or in a short time. However, it fails when beta becomes larger, reaching the relative error of almost 100% for beta greater than 10. Besides, for chaotic system, there is almost no relative work about pins. First, it is sensitive to initial values. In addition, some perturbations may have a huge impact on solution. For example, for the famous Lorentz system, the dynamics of the Lorentz system demonstrates the chaotic behaviors for parameters sigma equal 10, rho equal 28, beta equal it's we use pins to deal with these problems. Also, we consider exactly imposing initial conditions and follows by changing the final output of the network. The results show that although initially solution approach well, it quickly deviates from the exact one. Okay, come back this question. For the dynamic systems, using numerical methods such as the over method, we have the following iterative scheme. We can see the value of the previous time affects the value of the later time. Where most of PINs methodologies typically combine spectral information X and temporal information T and network inputs, overlooking temporal dependencies across previous or subsequent time steps. Like the Lorentz systems, the values and the time points taken are treated simultaneously. If the solution and the previous time is not treated well, the one and the lead time is difficult to train. This is also why PIN always fails on long training time. Some people have noticed this question of pins, and there have been some techniques to solve this question. For example, the sequence-to-sequence learning text was proposed in 2021. In contrast to regular pin training, the solution in sequence-to-sequence learning is predicted for only one dirty step and the time. Then the predicted solution and t equal to t is used as the initial condition for the next segment. Time domain division makes it easy to train pins in each domain. In fact, this is actually continue to train the solution in the next domain under the conditions that the solution and the previous domain is sufficiently close. Besides, one proposed the choral training for pins. They also found in pins the residual loss LRTI will be minimized even if the predictions and TI and previous times are inaccurate. This behavior inevitably violates temporal causality, making the PIN model susceptible to learn error solutions. So they designed a weight WI. WI should be large and therefore allow the minimization of LRTI. Okay, so we should design a new structure for PIN to deal with sequence to capture the relationship of solution at different times. Speaking of sequence learning in machine learning, the first thing that comes to my mind is recurrent neural networks and the special recurrent neural network, long short-term memory induced memory unit and gate mechanism. It is made to solve the problem of gradient discipline and gradient exposure during long sequence training, but they can't avoid the log structure. Using an encoder-decoder, convolutional long short-term memory network is proposed for low dimensional spatial feature extraction and temporal emotion learning. Also, onto the log structure, it's difficult to train. Okay. In current years, transformer, deep learning model architecture for natural language processing and other sequence-to-sequence text was first proposed in 2017. If you don't know transformer, you must have heard of ChatGPT. GPT means generative pre-trained transformer. Transformer contains an encoder block and a decoder block. Encoder block is a stack of exactly same encoders. Decoder has a similar structure. Okay. In fact, this is a structure of sequence to sequence. For example, sentence in one language embedded into high dimension spaces, translated to another language embedding after stacking multiple layers of the same model. This is encoder and decoder. So what's that in the encoder? An encoder consists of multi-high attention and fully connected neural network. The transformer architecture introduced a self-attention mechanism, a key innovation that make it greater when working with sequence data. Just like the title of the paper, attention is all you need. Here, used is scale dot product attention. Scale dot product attention means that we have three parts: query key and value. For given input sequence U, self-attention computes the output sequence O from the query key and value vectors, which are obtained from a weight matrix. Here we use three transformation: FK, FQ, and FV. If they are linear, they are weight matrix. Compared with recurrent structure, transformer is superior in quality, will be more parallelizable and require significantly less time to train. Also, alternative self-attention mechanism, including the additive attention, coarse attention, and Fourier attention, have been explored to improve performance. For example, coarse attention performs feature extraction on two different modes of data, like text and images. We do not go into detail here. Recurrent research has explored the use of attention mechanism for various machine learning tests, particularly in solving and predicting differential equations. For example, using transformer decoder to predict physical models. And also, no graph transformer framework was proposed, which uses graph transformer with modular input encoders to directly incorporate differential equation information into the solution process. And the transformer based framework transformer, combining transformer structure with PIN for solving PDEs. Okay, most of them just usually imitate the structure of the transformer without sufficiently theoretical foundation. In contrast, we would like to propose an advanced network structure by stacking self-attention blocks behind the pre-trained pins such that our neural network can effectively capture the correlation of solution sequences of PDEs. So we design the AttnPINNs, which consist of 5 components of its architecture. A sequence operates pre-trained pins, dimension left mapping, self-attention layer, and output layer. This is the architectural overlooking overview of AttnPINNs. Okay, let's introduce each component in detail. Component 1 is sequence operate. Because self-attention is concerned with sequence relations, firstly, we design a sequence operate G. This operate is tested with transforming inputs from special temporal points into sequence formats. Here we present 2 schemes for the sequence operate. Of course, there can be other suitable definitions. Where T and alpha are hyperparameters, inherently determine how far the associated position is from the original point. And besides, the definition of G2 shows that we take into account not only temporal dependencies, but also spatial dependencies. And it is always that the range of operate G1 is contained in the range of G2 when hyperparameter T and alpha satisfy certain conditions. In practice, this should not be set to very large scale. And larger values of T or alpha have the potential to weaken the dependencies between adjacent discrete time steps. Then we need a pre-trained pins, which is in a good approximation around the initial value of PDs. In practice, it is easy to implement since we can take the weight of the initial condition loss term sufficiently large when training pins. Then the temporal sequence are submitted as input to the pre-training pins, and the output sequence are obtained. The component 3 is dimension left mapping, which increases the dimension of the output sequence to a higher dimension to enrich the information content within each vector. It can be easily implemented by a linear mapping. Component 4 is self-attention layer, which consists of a number of identical self-attention blocks with residual connection. It should be noticed that the self-attention block is exactly identical, not only in structure, but also in parameters. In transformer, encoder block is a stack of 6 exactly same encoders, but their parameters are different and both need to be trained. Here, although we have many attention blocks, the number of parameters is small. Okay. Finally, we contrast an output layer to map U from the high dimension to the original dimension. Such the value of solution endpoint IT can be obtained by taking the last element in the sequence. This is the algorithm framework of AttnPINNs. We still use the loss function of pins and one of the AttnPINNs. Then we can optimize it by ADAM or LBFGS. Also, we present the convergence analysis of the AttnPINN to guarantee its effectiveness.
And can you go back and we want just to check the algorithm a little more carefully? Can you go over the steps slowly? The algorithm?
This self-attention layer?
No, the algorithm, the table, you have the algorithm. Just go step by step, please.
Yes.
No.
The table?
Well, you had the algorithm, the pseudocode.
Really code. Okay.
This one. Yeah. Can you just go through the steps? Didn't have a chance to read it.
Okay. Firstly, we should design the sequence operator G and use pin to obtain the pre-trained pins UP and determine the number of self-attention blocks M and outlier P, just like this photo. This we determine N is 3 and M is self-attention blocks. Then we should obtain the points and by let's see. Let's see. Yeah. We have XT and through the sequence operator G, we can obtain the sequence format. Then they submit to the pre-train pins, and then we can design a dimension lifting using a linear matrix WL. Then the obtained sequence can be submit the self-attention layer. We designed the number of self-attention is M. Because we obtained a sequence format, so we if we want to obtain the point xt, so we take the last element in the sequence in the last sequence, because we design the sequence operator G is this format. Okay, we obtained the value and xt. Then using automation diffusion, we can design the loss function. I think with pins. Then we can use optimizer DAM LBLGS to minimize it.
What is K? How do you choose K, the maximum number of iterations in the last block?
Okay.
K. For S equals 0 to K, it says maximum
each
iteration
number.
How do you choose that? Is it 1? Is it 10? Is it 100? Is it a million?
First we determine K equal 500 500,000.
500,000.
Yeah. Because we use the LBFGS and about some question maybe different because we
so K is the
focusing on
number
different.
K is the number of iterations of the optimizer. Okay.
K. Yeah,
And every
the-
time you update the, you add the attention. No, for every block, sorry. So maybe you can go back to the architecture and explain the method in the architecture. Go back a couple of slides where you have these colorful blocks.
yeah.
No, the
This
previous one, the
self-attention layer.
overview, where they have the plots.
This
Here, yeah.
this
Maybe you
figure.
can explain here, yeah.
How to determine M, the
No,
attention blocks.
just explain the method, your method. Explain your method using this visual.
It's just like this framework. Firstly, we determine the training points, then submit the file component, sequence operator, pre-trained pins, dimension left mapping, and self-attention layer. You mean how to determine the self-attention?
I don't understand the
number?
workflow. I don't understand the workflow. Maybe somebody else understands. I can explain it.
You mean why design this framework?
No, I think
About
that the question is how can you explain how your algorithm works? Like what is happening? Like for example, here you send the data to the pre-trained pin, right? And then what happens?
But what does pre-trained pin means? Pre-train how?
oh, this pre-trained pins?
Yeah, how did you pre-train it?
Yeah.
Maybe Zhenya, the professor could explain it. I don't understand what's going on.
This pre-trained pins is a good approximation with output around the initial values of P. We can when training pins, we can determine the
So you mean the
determine
vanilla pin, for example, or no enhancement? I don't. What is pre-trained
yeah,
pin?
this is a vanilla pin.
And what
Just
is
we should
around the initial value of PDs? So just the initial conditions. I don't understand this terminology. Panos, I think you said you understand. Can you explain it?
We can determine the parameters by training. The loss is same as a pin. But we choose the
Juan, can you let Panos? Can you let people talk? I think you muted everybody from, so they cannot unmute.
Actually, I'm trying to ask him to unmute, but let me.
Because nobody can ask questions.
Can
I
you
just
speak?
come on here. I think it is
here the
done.
public space. Okay, so I understand. Okay.
It is that temporal is divided and then it looks like train in the first time zone and then goes. That's the P10 part. Like here it is written then temporal sequences. So it's look like the P10 is trained for the first time zone.
Maybe we should let the advisor explain to us. Professor Zhenya Yan, can you explain the workflow for us? Can you unmute him, Juan?
I think that everybody can speak. Jenya, can you hear us? Kamal, you could unmute yourself, right? You could talk.
Hi, just it look like that it's divided to number of time temporal sequence, and then first part is like train in the first time zone.
Yeah.
No.
He means he chose the maybe a good initial condition and use the pin. Yeah, I think.
The
Firstly,
format
we should
is
choose the better initial condition to solve the PD. Use the pins.
Can you go back
Can you go
to
to your sketch?
Yeah, can I go to the sketch? From the sketch, you can tell us. Maybe you can go to for the sketch, the schematic, the figure.
figure. Yeah, this figure.
Okay. So can you like workflow means from step one, step 2, step 3. Just show with your cursor. Maybe you can explain here what's going on. Not what we think, but what you are doing actually.
We can continue. Then we will talk about this workflow. Then we can see that by the convergence analyze. Okay. The convergence analyze of the AttnPINNs to guarantee its effectiveness. Here we prove it when du equal 1 and don't consider the dimension left mapping. We write the equation in the evolution form for the convenience of the following proof. Firstly, the assumption is cleared, which means that we have successfully approximated the initial condition data by pins. This is the pre-trained pins. In practice, it is it can be implemented since we can take the weight of the initial condition loss term sufficiently large when training pins. Okay. Speaking of self-attention, some people may ask what exactly is mechanics. In the realm of dynamical system, self-attention closed resembles numerical time integration methods. Besides, compared to traditional numerical method, self-attention provide a significantly great capacity for learning the time integration techniques. The following demonstrates this fact. For the dynamical system, we can use nth order explicit damn best-forward method time integrator to solve it. In fact, we can prove a self-attention block with a residual connection can approximate explicit time integrator within arbitrarily small error bound. Going further, the same holds for linear system of the form equation 1. This is the proof of the lemma. Let me game this. Okay, according to assumption 1 and lemma 1, we can prove the following convergence theorem for AttnPINNs. We can see the error can be controlled by the 3 parts. The first term is due to numerical errors, where we use the nth order explicit damn best-forward method. The second one is caused by self-attention layer, and the third one is due to pre-training pins error. The basic idea of the proof is that near the initial value, the pre-training pin is close to the exact one. Then through M self-attention blocks, which is similar to through the numerical iteration, the solution is totally corrected. Okay, let's skip the specific detail. Okay, let's skip this again. Okay, let's start here. Also, we verify the effectiveness of the AttnPINNs method by experimenting with a wide range of PDEs, especially in the multi-scale, high frequency, and the chaotic problem, including the chaotic Lorentz system, the convection equation, and the wide dimension.
Jin, so 1 second. I think that Jun Yang Mao has a question.
Yeah, may I ask a quick question? So could you explain how do you take the partial derivatives of the output with respect to the input? You have the pin loss in your loss function, right? So how do you take the partial derivatives? Could you explain a little bit how the partial derivative go backwards through the self-attention blocks?
You mean how to determine the loss?
Yeah. Do you have PDE residual in your loss?
Yeah. We
So
use
how
the
do you calculate the derivatives?
we use the automation deviation
So
because
it can. So basically, you take the backpropagation with respect to the input coordinate, and it can go through all the blocks. Is that correct?
in fact, we obtained an sequence. The point. We can see that. We can choose n points. Then the sequence operator we can obtain the n times n times sequence. In fact, actually we in the end we obtain the sequence at these points. If we want to obtain the values at xt, we can choose the last elements because we design the sequence of G as follow.
So what you are trying to say is that your partial derivative is only on the xt rather than the xt1, t2, t3. Or the
Oh no. In the end, we obtain the value is about xt. It's not about the x1 ti x2 and this. So by automation division, the output has the output u is about it's a function of xt. Okay, we continue. The moment we demonstrate the advantages of our method in terms of accuracy and efficiency compared to the AttnPINN and other advanced deep neural network architecture, including quadratic residual networks, first layer sign, and transformer. Table 1 exhibits the hyperparameters of AttnPINNs for different physical models. The main results are shown in the following table. Most of the examples fills with the winner pins. And the order of magnitude of the loss shows that they mostly fall into a local minimum. In contrast, the AttnPINNs can overcome the challenges, especially compared to the best results between the winner pins, QIS, FIS, and the pins former. The AttnPINNs can achieve up to 90% improvements in some examples. In some examples where some advanced methods perform well, our AttnPINNs method is also able to further reduce the error. On the other hand, according to the loss and maximum iteration number, the AttnPINNs can achieve a smaller loss with a short number of iterative steps. These are other examples. Okay.
Well, wait a second. Let's look at the numbers. Just leave it here so we can look at the numbers. You're not explaining right.
Explain this.
What's the interval? How long you integrate? What's the total integration time? Is it
the time is after we will talk the training cost about
not
time.
the computational time, that the integration time for the problem, for the PD or the ODE? 0 to, you go from t equals 0 to t equals what for these problems?
You mean the t the time we design the time in interval?
Yes, the time interval.
Oh, okay.
For the Lorentz system, for example, how long you run? T equals 1, t equals 10.
We can see this example, the Lorentz system. Firstly, we experiment different time interval. This example, first we choose t equal 1.5. As you can, we can see the predicted solution is close to the exact one for t equal 1.5. But we want to obtain the for a long time.
You do sequential training. I see. Yeah. Okay.
Yeah. We also split up the typical domain into many subdomains and train network to learn the solution in each subdomain.
Then you go back to the second table.
Second table. The convection.
The next one. Yeah.
About example, the NS equation, we text t equal 0.5 because it is in the regime.
I don't think you're comparing with the state of the art, right? One, I think it was Alan Khan, right? Or Elham. These are not state of the art results.
Yeah, I think with RBA for Alan, you can go a little bit lower than this. Like, no, for with Panos method, they get to 2 to the -5 if I'm not wrong.
The weights, right?
Yeah, with Panos weight.
You usually use
but if I may,
they use.
But if I may say something, like the error for for burgers looks nice. That one you should.
Yes. Because they designed the method focusing on different equation. We only use the new structure without any other techniques such as depth sampling or other optimization
Well, if
method.
you look at the Varghese, he cuts the error by a factor of 2 compared to vanilla pins.
Yeah, I think that this is also a bit misleading because I think that he's not reporting relative L2 error. So it's a bit hard to say.
Yeah.
Because it's not relative, right? So it's
The Burgers equation?
Yeah, on all the results you're reporting the loss. When you say RM mean is relative mean absolute error is what you mean here?
Yeah.
Relative.
It's
This R means relative?
yeah, it's me relative mean
Absolute. And then relative
error.
mean squared error. Okay, then actually even the normal. Yeah, I think no even with that case. Yeah, you can get much lower because with Panos method or even with all the RBA, for example, for Aldecan, you can go to 2 to the -5, 3 to the -5. Yes, but there's some improvement against the normal pin, I guess.
Please proceed.
Okay.
I think that Shungyang has another question.
Yeah, just a very quick question. So for the Navier-Stokes result for the first column, your pins, have you tried the sequence to sequence, or we call the time marching method, that slice the time domain to multiple subdomain and using multiple networks to fit them?
Actually, use the photo chain. In fact, they also divide time into subdomains. But they use subdomain interval just about 30 equally small. In fact, in this method, we can determine the 30 more larger than the UA method. For the next example is a convection equation. The equation has a simple analytical solution for predict boundary condition. The pins is unable to achieve the good solution for small values of convection coefficient. Here we set the large convection coefficient beta equal 50. These are the results for different methods. We can see that it's difficult for the pins, QIS, and FS to effectively learn the global solution due to the highly complex and high frequency pattern. According to the training plot, the loss is optimized to log minima and compared with pins format. The AttnPINNs can achieve the low training loss and test error after fewer entry steps. The improvements with respect to ME and IMC are about 30% and 28%. Results shows clear advantages of the AttnPINN in terms of performance, S3, and convergence speed.
Jin, one quick question for this. In this case, for these iterations, I think that you already said it before, but just to make sure, what was the optimizer that you were using, Adam or LBFGS?
Yeah, we use the LBFGS.
Oh, directly LBFGS. So you're in double precision too?
Only LBFGS. But
Okay.
we train the learn system because it is loss function drops from a large values around 1,000. We first use 10,000 steps diameter optimization.
Okay, great. Thanks.
Okay. Okay. Next, we give some also analyze. We aim discuss the effect of hyperparameters and training cost. Firstly, we discuss the impact of two important parameters: sequence length n and the number of self-attention blocks m. According to the series 1, we know that the sequence length n, which is the context window of self-attention block, has a great impact on the convergence error. In turn, the number of required self-attention blocks is affected by n. Intuitively, larger values of n and m tend to result in smaller errors. However, experiments show that that is not always the case. We show the effect of the hyperparameters n and m on the RME and RMC by solving convection equation as an example. In general, the larger the value of n and m, the smaller the relative error is, and the smaller n tends to require more self-attention blocks for the algorithm to converge. However, more self-attention blocks are not always better. A large N means a deep network, which leads to optimization difficulties. And for example, the RME and RMC are this for n equals 7 and m equal 8. Therefore, n equals 7 and m equals 7, the relative errors are smaller. Furthermore, for fixed m equals 6, we gradually increase the value of n from 1 to 8 and find that the error drops to the order of 1 to n greater than 4, but it is not monotonic with n. Therefore, it is necessary to find the box rate n and m. An additional factor to take into account is computational and memory cost during training. The memory overhead of AttnPINNs mainly lies in the sequence generation and the self-attention block. Compared to the traditional method, the chain points of AttnPINNs are more, and the self-attention block contain 3 neural networks. Unfortunately, the M self-attention blocks are identical. And to show clarity, the hyperparameters and training cost for different methods are exhibited in table, and the computation relies on solving the analytic equation. It can be seen that our approach requires fewer parameters to train than pins format, and compared to the pins and FS, the number of training parameter is about double, which is acceptable. In addition, for the pins format, the key query and the value vectors are the input of the previous steps. In fact, we can also fix F key and FQ to be the identity map to further reduce the cost in practice. And for time cost, the AttnPINN method is more expensive than other methods. For example, we observe an approximate triple rise in time cost to train and steps as a pin form. However, considering that the number of chain steps for the AttnPINN is much less than other methods, the time cost is acceptable or even lower. For example, this figure displays the plot of training loss with time for solving the analytic equation. You can see that for the same training time, the loss for the AttnPINNs is smaller. Furthermore, the time overhead mainly lays in optimizing the deep self-attention layer. Based on the results in the previous subsection, we could reduce the number of self-attention blocks to speed up the training. Okay, finally, we give the summary. In this work, we propose a new network structure called AttnPINNs to capture temporal dependency between solution sequences. Using it, we can obtain a global solution for PDs. And the self-attention provides a significantly great capacity for learning the time integral techniques. We prove that a self-attention block with a residual connection can approximate an explicit time integral within arbitrary small error bounds. With it we provide a proof of the convergence of our method. Also, we demonstrate the AttnPINNs by a wide range of PDs whose solution tend to have abrupt changes or exhibit the odd scale high frequency. And the numerical results exhibited that the AttnPINNs can capture solution structures and output most of the other strategies. Finally, this is a summary of future work. There are two things I think worth exploring. In fact, we only propose a new network structure, not consider the other techniques such as sampling strategy, adaptive ways, and optimization strategies. In practice, AttnPINNs is easy to incorporate variant learning schemes to achieve better results. The second direction is about to redesign an attention mechanism algorithm suitable for high dimension. As we know, in high dimension, due to the influence of network structure and inputs sequence, memory cost is larger than the general method. In order to overcome the cost of dimension, we designing an attention mechanism algorithm suitable for high dimension our future work. For example, we can use the tensor product structure or tensor neural networks to redesign our fully connected deep neural network. Okay, that's all about my presentation. Thank you for listening, and I'm happy to take any question. Thank you.
Thank you so much, Jin Song. Do you have any questions from the audience? Maybe I have a short question. Do you have this paper on arXiv already, or do you have it it's already published? Because I will try.
This paper and not published.
Okay, yeah, because I was trying to look it a few minutes ago and I couldn't find it. Okay. Yeah. Do you have any other questions from the audience?
Yes, I have a question.
Yeah, please.
Yeah, I'm Chen Zhang, a postdoc in at Brown. I have a question about the second item in this slide. So you said your self-attention is related to the time integration, and I think you designed this self-attention mechanism to better resolve the time-dependent problem. Can you briefly, maybe based on the figure, I mean the structure, can you briefly, how does this self-attention works? I mean, what is so attention to what? What is focused here?
The attention, how So the work is based on the lemma. In fact, the scale dot product attention is according to the this calculation. We can choose the core Q key and V in this in the following format. Also, it is with it is with the residual connection. In fact, we choose the KI, KG, QG, and VG in the format. We can find the output is exactly to the Adams space for method.
Okay. I'm not familiar with this formula. So based on my understanding, the self-tension is some kind of way to adjust the weight, right? So could you please, based on the figure, the structure of your model, to say after adding this self-tension mechanism, which part is the weight of which part is increased and the weight of which part is decreased? Am I clear?
Yeah. In fact, the optimization is to optimize these parameters. It's BJ, FJ, FQ, F. The FQ, and FV we define is are all the fully connected neural network.
Yes.
So the FV can optimize the
Maybe can you try going to the sketch of your architecture?
Yes.
this table.
Yes, maybe here. Can you explain us what is? Jen, maybe you can.
Just
Yes.
like the
So I think that here, Jen, your question was like here, how is the attention working, right? That was if I
Yes.
understood correctly, right?
yeah. The self-tension work.
Yeah, so this self-tension, by this self-tension blocks, what is emphasized? Which part? Yeah, which part is you have a higher weight? So focused on what?
Effectively, we should first design the parameter M.
Yes.
In the theorem one, in fact, M is should very large, but in practice, we can in continue determine M equal about 10.
Okay, so I think the key issue is the time series, the time sequence, right? So maybe you focus on some time steps, or
No. We the time sequence are obtained according the sequence operate.
yes.
In fact, the training process, we usually use many points because the sequence operator is generate from one point to generate
Yes.
n point.
Yes.
But in the end, according to the output layer, we choose the last element in the sequence. That's the output.
Okay.
So it's like your attention is like what moves you forward in time, and the attention will tell you what parts of the previous step is the one that you should focus on, or something like that. Yeah, so you have your pre-training, right? You get some initial time, and then you expand the dimensions, and then you use these attention blocks to move forward in time, right?
But this prediction pin is the same with the vanilla pin. We just choose the weights in those initial ladder, and in this process, we can hold the parameter is unchanged in the pre-trained pin.
Okay. Okay.
Yeah. So another question. So if you do an inference, which part do you use to make an inference?
Inference?
Yeah, not about train. After training, when you want to do a prediction, which part are needed to do a prediction?
This work is not about prediction, because
but it has some errors, I think. So which part do you use to make a error estimation?
Firstly, by numerical method to obtain the numerical solution.
Yeah. That's a true solution. But how? Where's your prediction of your neural network?
Where's my prediction?
Yeah. How do you? So after training, say if you
Yeah.
want to calculate the error, which part of your neural network is used to calculate or to make a prediction? Yeah, so you said the pre-trained pins is fixed, right? So I think maybe
subdomain.
Yeah, I think your pre-training pins are fixed during training, right? The weight will not be so. Which part are you training, and so all of the parts are going to be used when you want to make a prediction?
Just the parameter in the dimension mapping and the self-function layer?
Yes. So if okay, so if you want to make a prediction, you should give X, Y, Z, and P to the pre-training pins and get the result from output layer.
Yeah.
Okay.
The dimension, the parameter is fixed up to training.
Okay, got it. Thank you.
Okay. Thank you so much, Jin and Jinja, for your time today. Thank you so much for sharing your work, Jin. If you can, please let us know once your paper is on archive, so we can take a look a bit more into detail into the details. We have.
We should close the share.
Yes, please. Thank you. We have another 2 speakers, so I think that.
Thank you.
Thank you so much, Jin. Vivek. Okay.
Hey.
Hi. Okay, great. Hi, Vivek. Let me see. Let me make you. Now you should. Could you please help us trying to share your screen?
Yep.
Great. Yeah. Okay. Now this works. Okay. So our second speaker is Vivek Oommen. He's the 4th-year PhD student at Brown University, advised by Professor George Kanedakis. Before joining Brown, he completed his undergrad in mechanical engineering with integrated masters in data science from the Indian Institute of Technology in Madras. Vivek, with this short introduction, the floor is yours, and you can start whenever you're ready.
Yep. Thank you, Juan. So today I'll be presenting our recent work on improving the spectral bias in neural operators with the help of diffusion models. So I'd like to begin by a brief introduction to neural operators. So in neural operators, we try to approximate a mathematical operator with a trainable neural network G parameterized by theta. So if this N is the operator, which is a mapping from a family of functions U to a family of functions V, we try to approximate N with the neural network G parameterized by theta. Theta are the trainable parameters. So in the context of learning time-dependent operators, we can train a neural operator G to learn the mapping from the state of the system at t, u at time step t, to u at time step t plus delta t by minimizing the norm of the error between the solution and the prediction accordingly. So yeah, this is a brief introduction, and I also want to quickly go through one of the neural operators that we developed in our group. It's called MACHO, which stands for Multi-Scale Attention-Based Time-Conditioned Hierarchical Operator. So the MACHO's architecture is inspired from the neural networks architecture used in the denoising diffusion probabilistic models. And it combines the units that had a lot of success in biomedical image segmentation with the attention blocks from the transformers that is often used in the language modeling tasks. So essentially, you can see a unit with attention blocks and time conditioning mechanisms in a MACHO. And I just want to quickly go through one test case that we used in MACHO and then dive into the main topic of this talk. So here we tried to model the flow past a double cone geometry, and this is the domain of interest highlighted in gray. We see that the true simulation was performed with using a solver called Trixie by Ahmed, who is one among the audience. And the first row represents the ground truth data or the solution. And in the second row, we show the solutions predicted by MACHO. And here you can see the zoomed in versions of the true and predicted solutions at different time steps. So the point is that MACHO can effectively learn solutions with interfaces or high spatiotemporal gradients. And it also captures the shock-induced circulations or the vortices near the surfaces of the double cone geometry. Yes. Now, after this quick intro on neural operators, I would like to dive into one of the difficulties that we encounter while training neural operators. It's called the spectral bias in neural operators. To explain this, I would like to show you a screenshot from the Fourier neural operators paper. So here, the first row represents the vorticity field corresponding to the vorticity stream function formulation of the Navier-Stokes simulated using a pseudospectral method. And you can see the first row is the ground truth and the second row is the prediction of the FNOs. And this is a screenshot from the FNO paper. And as you see, for this relatively smooth initial condition, the solution coming from the solver and the solutions predicted by the FNO aligns very well with each other, as you can see here. But the problem lies if you change the initial vorticity to make it less smooth than what is shown earlier, then in the ground truth solution itself, you'll start seeing these smaller artifacts or smaller features or finer features with higher wave numbers start occurring in the, sorry about that. Yeah, starts occurring in the solutions. And when you train the neural operator to learn this, then you will have issue because in general, the neural networks have difficulty learning solutions with high frequencies. So these high spatial frequencies are very challenging for the neural operators to learn. And for the specific case of FNO as shown here, we can see from the power spectrum as well that it is missing out on the finer features like the finer details and it's also giving rise to Gibbs oscillations, this artifacts over here. So if you look at the energy spectrum of each of these images, so corresponding to, if you look at column 1, the first column, at time step t equal to 12, you have the ground truth simulation and the FNO's prediction. If you take this image and take the energy spectrum of these images, black being the ground truth and blue being the neural operator, you can see across all time steps for each of these images, the energy spectrum of the neural operator is significantly below that of the ground truth. And you can also see a quick increase in the energy towards the higher wave numbers, indicating the Gibbs oscillations kind of phenomena in the in the FNO's prediction. So this is the one of the limitations of the neural operators in the current setup. So how can we address the spectral bias in the neural operators? So this is the crux of our work. So our approach is as follows. First, train the neural operator as usual. That is, given the state of the system u at time step t, train the neural operator to predict the state of the system at time step t plus delta t in the regular data-driven manner. After you train the neural operator, freeze the neural operator and use it to condition a score-based diffusion model. So basically, you have a pre-trained neural operator that has been frozen. Its output is concatenated with a noisy image, and you train the diffusion model to predict the less noisy version during the training stage. And then after the training, you try by minimizing the score function. And after the training, you can sample using the diffusion model. So essentially, this is a conditional sampling of a score-based diffusion model conditioned on a pre-trained neural operator as its prior. So this is the overall approach in one slide. I hope I'm clear till now.
Yes. So Vivek, this is Lulu. So here the diffusion model works as a way to correct the prediction from the pre-trained neural operator, right?
That's correct, Lulu. Yes. So we have like a low fidelity or a over-smoothened solution coming from the neural operator. And we utilize this solution as a prior to condition the new diffusion model. And based on this, then we perform a conditional sampling using the diffusion model, utilizing the information learned by the neural operator. That's exactly correct. Yes.
Okay, got it.
Yeah. Thank you, Lulu, for the question. Yeah. So here is the Kolmogorov flow test case again with the less smooth initial vorticity. So the ground truth again is coming from the same pseudospectral solver. And you have seen the first row and the second row before. Second row here being the Fourier neural operator. Now, in the third row, you can see the output of the diffusion model conditioned on the Fourier neural operator in this case. And then again, at every time step, we are performing the we are computing the energy spectrum and plotting it here. So as earlier, the black and blue doesn't align well, but the red curve corresponds to the energy spectrum of the diffusion model conditioned on the neural operator. So for all the time steps, we can see the energy spectrum of the diffusion model has a much better alignment with the ground truth than the neural operator alone. So specifically in this case, we see these finer features are being recovered. And we also observe that these artifacts, you can see this, if you look closely, you can see these artifacts in the Fourier neural operator's prediction because of the Gibbs oscillations. That's also being filtered out or cleared by the diffusion model. So we again tried the same experiment, but this time instead of using a Fourier neural operator, we tried to use a regular unit for this task. And for the unit, you don't see the Gibbs oscillation specifically, but still it exhibits the over-smoothing. And the diffusion model again works well, conditioned on the unit as the neural operator. And here are the energy spectrums. We also do the same experiment with Macho. And again, Macho also does a good job. But again, if you look at the earlier time steps specifically, we can see these features are a little bit over-smoothed even in the Macho's predictions. And the diffusion model helps to recover the missing frequencies. So to dive a little bit more deeper into what we are doing, so we are performing a conditional sampling. So here I have a figure A and figure B. So in both the figures, the horizontal axis corresponds to the physical time t, which is the time parameter in the PD. and the vertical axis corresponds to the diffusion time step j. So at every time step, at every physical time t, you need to sample using, you perform the conditional sampling of the diffusion model conditioned on the neural operator. So at the 0 or the first diffusion time step, essentially the output will be just a noise. So, and the corresponding energy spectrum can be seen on the right. So the black being the ground truth and the red being the output of the neural operator plus the diffusion model at the 0th diffusion time step. So eventually, as you go down, as you perform the sampling process, you see the denoising diffusion model get rid of these noise and eventually learns to predict the right solution. And we can, on the right side, you can see statistically the energy spectrum aligning very well and eventually falling in place by after 32 diffusion time steps. Yep. And we also perform a POD analysis because in the energy spectrum, the spectrum is computed just from one image or one time step or the one state of the system at a particular given time. So here we perform the proper orthogonal decomposition analysis in which we take the 10 time steps predicted by the neural operator, the 10 time steps in the ground truth solution, and the 10 time steps estimated by the diffusion model conditioned on the neural operator, perform the proper orthogonal decomposition, and on the left you will see how the eigenvalues change with the different values of the index I, and on the right I show the eigenmodes that corresponds to the dominant 9 eigenmodes corresponding to the 9 steps of the ground truth, neural operator, and the diffusion model. And you see a better alignment between the first and the third columns for all the modes. Okay. Next, we tried to apply the same methodology on a buoyancy-driven transport problem. So here we directly utilize the data from the PDE Arena benchmark, and this is from the paper by Gupta and Brandstetter. And here we have a scalar field, like a concentration field, that is transported by a buoyancy-driven flow. And you can see the ground truth on the first row, prediction of the neural operator on the second row, and the prediction of the diffusion model conditioned on the neural operator on the third row, and the square root of the energy spectrum on the last row. So one point to make here is that if you go through the paper by Brandstetter, you will notice that you can indeed get the high frequencies correct by using a unit alone. So in this context, the neural operator is a unit. So if you go through their paper, just using a unit, you can recover the high frequencies. But in this paper, they are able to achieve that because they train a unit with close to 300 million parameters. However, when you try to use a smaller unit with 2 to 3 million parameters, again, the spectral bias becomes an issue, and you will see this over smoothing in the predicted solutions. So again, we train another diffusion model also with just 3 million parameters, conditioned on the trained unit as the neural operator, and we are able to recover the higher frequencies. So instead of using a 500 million unit, we just use a 3 million unit and a 3 million diffusion model. So 6 million instead of like 300 to 500 million parameters. So again, the same methodology and the energy spectrum and the states from the two different approaches. Next, we tried to see how well the neural operators can, or our approach can work on modeling a turbulent wake of an ARCA 0012 airfoil subjected to a flow with Reynolds number of 23,000. So we directly utilized the simulated data or the flow simulated using Charles, which is an LES solver developed, and the data was directly downloadable from this particular paper, a database for reduced complexity modeling of fluid flows by Town et al. And here, given the time step t, we tried to predict all the way up to 50 taus ahead, where the tau is the convective time step, and 50 tau corresponds to 78% of the Strouhal period for this case. And here you can see the ground truth from the Charles. Prediction of the neural operator is clearly over-smoothed, and the prediction of the diffusion model conditioned on the neural operator. Yeah. Then, yeah, one thing I need to stress is that, so in the neural operator, you need, after training the neural operator, you just need one forward pass through the network to predict the state. But in the diffusion model, because it's a sampling process, you need 32 forward passes through the network for the sampling. So essentially it is 30 times slower than the neural operator alone. But again, and in all the experiments we performed, we saw that the neural operator takes 0.01 second for one forward pass. So the diffusion model is essentially taking just 3 seconds. By 3 seconds, I mean for a batch of inputs. So still, I believe the 3 seconds is still much more efficient than directly using the solver. But yes, it is 30 times slower than the neural operator alone. Next, we try to apply it on a 3D jet with a Reynolds number of close to 10 power 6 and a Mach number of 0.9. Again, this is from the same paper by Town, and the flow was simulated using Charles. And in this context, the tau corresponds to the acoustic units, and we are predicting for up to 10 acoustic units ahead in time. And the first, here we show the first row represents the solution of the Charles, neural operators prediction in the second row, and the diffusion models prediction in the third row. And here the predictions correspond to the ISO surfaces of the Q criterion of the turbulent jet, and the color corresponds to the magnitude of the velocity vector. And here also, if you look at the energy spectrum at different cross sections at each of these different time steps, you will see a better alignment between the diffusion model and the ground truth compared to the neural operator. So far we have looked at simulated data sets, including the large D simulations. But next we wanted to look at how well it will perform on an experimental data set. So here we consider the Schlieren velocimetry of a round helium jet in air with a Mach number of 0.45 and Reynolds number of 6,000. Again, the experimental Schlieren data set was obtained from this work by Settles and Liberson. And this is a screenshot from their paper, and this is the experimental setup they are using. They have a jet that is flowing over here, and they visualize the jet using a camera, and essentially the visualizations using the Schlieren velocimetry visualizations corresponds to the density gradient of the flow. And on the first row, you can see the ground truth estimated by the ground truth captured by the camera. And again, the data set was like the raw pixels, like the images that you see here are actually raw pixels in the .tif format, the raw images, and we directly utilize the raw images coming from an experimental setup to train the neural operator, and then a diffusion model conditioned on this neural operator. So here you can very clearly see the over-smoothing in the neural operator, and the diffusion model is able to recover the frequencies, and the energy spectrums are shown here. And again, here we see that the energy spectrum doesn't go all the way till the dissipation state, but still the point of the spectral bias in neural operators and using diffusion models to address this issue is we are trying to convey that in this experiment as well. So yes, this here we applied it on raw images from direct experiments or Schlieren velocimetry of helium jet in air. And in this context, the tau corresponds to 1/6000th of a second, because that was the frame rate of the camera being used here. And yeah, in the future, we would like to explore if this helps in achieving longer rollouts, and if we can accelerate large eddy simulations and direct numerical simulations with this short leaps in time or short forecasts in time. And I'd like to acknowledge the help and the valuable insights and discussions from Dr. Andreas Robertson from Sandia National Labs and Alan John Varghese from Brown University. These are the references, and thank you.
Great. Thank you so much, Vivek. That was a really nice presentation.
Thank you.
Do we have any questions from the audience?
Yes, I have a question.
Ahmed.
So this is Ahmed from Brown. Very, very impressive, great results, Vivek. So
Thank you.
it was amazing how you captured those smaller scales.
Yeah.
So I have like two questions.
Yep.
One is regarding the experimental test case.
Yeah.
So the trained model can infer at any time, right? Like
So we are Yep.
so I'm wondering, like, using the trained model, you can generate a lot of instantaneous data, and then you can generate the average result basically. Yeah, so like the average statistics. Basically, you sample in time to create average statistics, right?
Yep.
You get the instantaneous result. You sample in time, and then you average it over time, and then you get a profile.
Okay.
So,
Yep.
like this neural operator can be used to generate that basically. Once
Yes.
you can train it instantaneous and then infer the average statistics.
Right. You can, because we are using Macho, which predicts the solution continuous in time, we can predict the state of the system at any time step between in the way we train. So in this context, we are given the state of the system at time t. We are training the neural operator to continuously predict the state at any time step between t equal to t and t equal to t plus 10 tau. So at any time between t equal to t and t equal to t plus 10 tau, you can get a low fidelity or an over-smoothened approximation using the neural operator. And then at however temporal resolution you want, because the time is continuous for Macho. And then if you use the diffusion model, if you train a diffusion model conditioned on this Macho or this neural operator, then you can recover the missing frequencies in a statistically similar manner. Yes.
And then I have like a second comment. It would be very interesting to try to learn Taylor-Green vortex test problem.
Yeah. Thank you. Yeah.
So
I make a note
if you want, we can work with that. I can generate some data because there, you're going from laminar to a turbulent flow.
Yeah.
And then you have a very wide range of scales.
Okay.
And then if you increase Reynolds number, then if this neural operator can learn that would be amazing.
Yeah. That sounds like a good idea. Yeah. Thank you, Ahmed.
Yeah. Thanks.
Great. Do you have any other questions?
Vivek, I had a small question on
Yes,
slide 22, if you don't mind.
Yeah, just give me 1 second. Yes.
I was just curious to know, like, some of these features, like these vortices that you see, like here, they seem to be like displaced in space as compared to the ground truth here. Is there a reason for that?
Yes. So you are doing a conditional sampling. So if you consider a one-to-one match, if you check a one-to-one relationship, it will not be there. So to be specific, if you compute like a norm of the error between just the neural operator alone and the diffusion model and the neural operator and diffusion model and the ground truth, then you might see the errors would be very similar, because there is some uncertainty because these frequencies are missing, and then we try to recover it from sampling. So of course there will be some offsets, like we discussed earlier with that bottle case. There will be offsets are expected.
I see.
So,
okay.
Yeah. Thanks for pointing that
Thanks.
out. Yeah. But it essentially brings the statistics to be very similar.
Okay. And one question in that part, and in that case, is it possible to use some kind of the tricks that people use, for example, for GANs or for diffusion models to make them look closer?
Can you say that again?
For instance, if you use GANs, in GANs you also get let's say you're feeding something, you get something from a sample from a probability density distribution, right?
Right.
Yeah, but for example, you can use tricks like reinforcement learning to ask what would be the seed that you would give you the answer that you're looking for.
Right. It could be worth exploring. That is true. And but essentially the thing is, like, once the neural operator gives an output, it is like a low fidelity output. So and it essentially gives rise to a one-to-many mapping because a lot of frequencies are missing in the neural operator's output. So it's like a super resolution task, which is a one-to-many mapping.
Oh, okay, got it.
Therefore, but still, that is an existing open problem, and it could be worth exploring. Yeah. Thank you for the question.
Okay. Do you have any other questions from the audience? If not, I think we can move to our third speaker, which is Alan, which was his picture was in this slide a few minutes ago. Alan, can you please try sharing your screen?
Yeah,
Let me
yeah.
make you co-host.
Can you see the screen?
Yes. Can you put it in presentation mode, please?
Yeah.
Okay. Our third speaker is Alan John Varghese. He's a third-year PhD student in the Fluids and Thermal Science in the School of Engineering at Brown University, advised by Professor George Karnadakis. Before coming to Brown, he had an integrated bachelor's and master's in aerospace engineering from the Indian Institute of Technology, Madras in India. Alan, with this short introduction, thank you so much for your time today, and you can start.
Thank you, Juan, for the introduction. So today I'll be presenting a work with Jin and Professor Karnadakis on symplectic graph neural networks to learn Hamiltonian systems and for node classification. So I'll start with the problem setup and the motivation. Then we will review symplectic maps and how they are relevant to Hamiltonian systems. And then we will look into our architecture of the symplectic graph neural network. And finally, we'll discuss the simulation results. So the problem setup consists of, so we have like n particles. So the n particles forms the nodes in the graph, and they evolve in time following some Hamiltonian dynamics. And for every particle, for every node, we store the momentum and position of that particle. So the momentum P is a d-dimensional vector, and the position Q is also a d-dimensional vector. The momentum and position of the system is given by this matrix. So here, P and Q are matrices of shape n by d, the momentum and the position matrices. So n is the number of nodes in the graph, and d is the dimension of the momentum and position of each particle. And our objective here is to, given the evolution of the particles from time t equal to 1 to capital T, we want to predict the evolution of the particles from t plus 1 to time t tilde. Essentially, we want to learn the one-step forward solution map that takes in the momentum and the position at the current time step and maps it to the momentum and position at the next time step. So this figure illustrates what we want to do. So we want to take in the momentum and position of all the particles at time step ht and map it to ht plus 1. So one prior work is called SympNets. So SympNets design symplectic neural networks that preserve the symplectic structure possessed by Hamiltonian systems. In other words, it bakes in the domain knowledge about Hamiltonian systems as a hard constraint into the neural network architecture. However, this doesn't scale well to high-dimensional systems or systems with a large number of particles. Whereas on the other hand, graph neural networks have been applied for particle simulations very successfully. For example, in this GIF is from the paper from the popular paper from DeepMind, where they use graph neural networks for fluid particle simulation. So graph neural networks possess a property called permutation equivariance, which basically says that it doesn't matter how you number the nodes in the graph. However, graph neural networks are not structure preserving. It doesn't have any domain knowledge baked into it. Essentially, SympNets are symplectic but not permutation equivariant, whereas graph neural networks are not symplectic but permutation equivariant. And our goal is to design SympGNNs that are both symplectic and permutation equivariant. So now I'll review what symplectic maps are and how they are relevant to Hamiltonian systems. So a linear map given by a matrix H is symplectic if it satisfies this particular equation. H transpose JH is equal to J. So J is this skew symmetric matrix. So this is for the case of a linear map. In general, a nonlinear differentiable map is symplectic if the Jacobian matrix of the map is symplectic. So you compute, to check if a nonlinear map is symplectic, you compute the Jacobian of the map, and then you plug it into the previous equation and see if it's symplectic or not. So why we care about symplectic maps is because the solution operator of Hamiltonian systems are symplectic. So this is shown by Poincaré in 1899. So this property of the solution operator being symplectic has been used to design numerical schemes that are symplectic. So they're called symplectic integrators, and they're more accurate for long-time integration, as shown here. So based on this scheme, we can see that we can look at this family of maps that are symplectic. So here P and Q are the momentum and the position. So T and V can be interpreted as the kinetic energy and potential energy. And this map is symplectic. So you can like take the Jacobian of this map and plug it into the previous equation and see that it's symplectic. Now we will look into the architecture of a model. So this is essentially what we had from the previous slide. So we look at what are called the low and up modules. So this is called the low module because it updates the lower part of the matrix. It updates the position based on the kinetic energy. And the up module updates the upper part, the momentum based on the potential energy. So Ti and Vi are the kinetic energy and potential energy, and they are parametric maps. So let's consider Ti first. So Ti is the kinetic energy. It takes in the momentum of all the particles. It takes in the n by d dimensional matrix and projects it to a real scalar value. And the potential energy takes in the position of all the particles and projects it to a real scalar value. And now we can compose these maps, the low and up modules. So for example, an architecture would look like this. So we can compose low and up modules. So the input is the position and momentum at one time step, and the output can be the position and momentum at the next time step. So here Ti and Vi are parameterized map, and how we define these parameterized maps leads to different equations, different architectures. So at this point, it just guarantees that this map is symplectic. However, in addition to this, if we can design Ti and Vi such that Ti and Vi are permutation invariant, then the map can be both symplectic and permutation equivariant. So essentially what it means is the node ordering doesn't matter. For example, the figure on the right illustrates that. So if we first do the symplectic map to update the positions and momentum to the next time step, and then if we permute the node labels, so here basically we're calling node 1 as node 2, node 2 as node 1. So if we permute it, and let's say we reach the state, alternatively, if you permute it and then pass it through the symplectic map, we reach the same point. It basically means that f of g of x is g of f of x. So depending on how we parameterize T and V, we can get different architectures. So we'll first present G SympGNN. So G here stands for gradient. So here the kinetic energy is parameterized in this following way. So we pass the momentum of each node through a fully connected neural network. We project it to a scalar value, and we sum it over all the nodes in the graph. In the case of potential energy, we project the position of two nodes that share an edge through an MLP to a scalar value, and then sum it over all the edges. So the architecture is illustrated on the right. So for example, in the low module, so plugging in this T and V into here, we get the update rules. So for example, in the low modules, we compute the kinetic energy, and then we compute the gradient of the kinetic energy to update the position. In the up modules, we compute the potential energy, and then we compute the gradient of the potential energy to update the momentums. So the drawback of this architecture is we need to compute the gradient every time we want to update the upper low modules. So computing gradient can be computationally expensive. And we would like to design an architecture which doesn't involve computing gradients, but instead does it based on some linear algebraic updates. So that takes us to the second architecture, LA SympGNN. So LA stands for linear activation. This consists of linear modules and activation modules. So this is a different parameterization of kinetic energy and potential energy. So for this particular parameterizations, we can compute the gradients analytically, and that leads to the update rules as shown on the right. So in the case of the low module, so this is the update rules at a node level. So in the case of the low modules, the momentum just gets copied over to the next layer, whereas the position gets updated based on the position, the momentum of its neighbors. So we look at the momentum of the neighbors, we project it to another space using a matrix KK, which is symmetric, and then we sum it over all the neighbors. Similarly, it happens for the up modules. So essentially here, the update rules are like message passing. So it just consists of linear algebraic operations, and we don't have to compute any gradients. And this is the parameterization for the activation layers. So the activation layers are as shown here. You can't just apply nonlinear activations like you do in general, because otherwise the map won't be symplectic. You want to guarantee the map is symplectic. So this is the activation modules. And then we can compose the linear and activation modules in an alternating fashion like this to get the architecture. So the input is the momentum and the position at the current time step, and the output is the momentum and position at the next time step. So with that, we'll now move to the simulation results. So our simulation results consist of two categories. So the first is to learn Hamiltonian systems in to Hamiltonian dynamics in physical systems. And the second category is node classification examples. So here basically we are it's like physics for graphs or AI for science for AI examples, where we use ideas from physics to solve challenges in graph neural networks or computer science. So this is the first example. So the system consists of 40 particles, 40 simple harmonic oscillators connected by springs in a straight line. And then so we use a step size of 0.01, and the first 500 data points are used for training, and the next 100 data points are used for testing. So the figure here shows the position and momentum of 3 different particles during testing. So the solid red and blue lines are the SympGNN. The dashed red and blue lines are SympNets, the prior work, and the solid black line is the ground truth. So from the figures, we can see that the SympGNN predictions aligns more closely with the ground truth than the SympNet. So in this plot, we show the variation of, and the leftmost figure shows the variation of energy with time. We can see that in the case of SympGNN, the energy doesn't vary much with time, whereas in the case of SympNet and in the case of SympNet, the dashed lines, the energy deviates much from the baseline. And the prediction MSE, the prediction mean square error, doesn't grow as much as compared to the SympNet in the case of SympGNN. The figure on the right shows the variation of mean square error with training size. So we can see that when the training data is small, the solid lines, the SympGNN outperforms the SympNets because of the inductive bias, because of the added inductive bias that the SympGNN has. The next example is that of the particles in 2D Leonard zone potential. This consists of 2000 argon particles and that are governed by the Leonard zones potential. So we use a step size of 0.1 picoseconds, and the training data consists of the first 10 picoseconds, and the test data consists of the next subsequent 10 picoseconds. The leftmost figure shows the evolution of energy with time. So the blue line is the baseline, the energy is almost constant. The SGNN, the SympGNN is denoted as using the orange line as SGNN. So the energy of SGNN predictions doesn't vary much with time, whereas the other models, the energy deviates from the baseline much more. The centermost figure shows the variation of the radial distribution function with the radius. So almost all the models closely match the baseline. And the rightmost figure shows the evolution of temperature with time. So here again, we can see that the SympGNN aligns more closely with the baseline. With that, now we'll move to the node classification examples. So here, we have like one static graph. So for every graph, for every node, each node belongs to one class. So here, for example, the color indicates the class that the node belongs to. And we have a feature vector associated with each node. The task is, given the labels, given the class that a number of nodes belongs to, we want to classify the remaining nodes based on like which class it belongs to. So for example, in the case of Cora dataset, each node has a 1433 dimensional vector, and each node belongs to one of the 7 classes. So here our approach is to take the position, to take the feature vector, project it using an MLP to get the initial position and momentum vectors, and let it evolve following the symplectic dynamics in the latent space, and then take the final position and map it to a 7-dimensional space corresponding to the number of classes, and finally use cross-entropy laws to train the model. So we perform experiments on 4 different data sets, and we compare it against other benchmark models. So the last 4 rows are variants of our architecture. The red indicates the best accuracy. The values shown here are the accuracies in node classification. So the red corresponds to the top accuracy, the green corresponds to the second best accuracy, and blue corresponds to the third best accuracy. So we can see that in all the data sets, our model is in one of the top 3 accuracies. In the case of squirrel dataset, we achieve like state-of-the-art accuracy. So in the node classification task, everybody, including us, does a lot of hyperparameter tuning. In our case, we use weights and biases, and the results are very sensitive to the hyperparameters you used. Therefore, node classification is not a good example of how good a model is. The node classification on the benchmark datasets. So we will further look at more robust challenges called the oversmoothing problem and the heterophilia problem. So to give some context about the oversmoothing problem, in general, deep convolutional neural networks are more expressive and they have better accuracies. So for example, in this figure, it shows the error attained by the best model in each year for the ImageNet challenge. So as we go further into the years, the best model attains lower and lower errors, and the depth of the model increases over time, like increases over the years. So the best model, the ResNet here, for example, has 152 layers. They're like very deep architectures. So in general, the motto has been the deeper, the better. However, the story has been very different in the case of graph neural networks. So for example, in this plot, we show the test accuracy with layers for different datasets and different models. So as we increase the number of layers, the accuracy drops substantially. This is very different from what we saw earlier. So what is happening here is a certain phenomena called oversmoothing. So for example, let this be the feature matrix. As you pass it through the layers of the graph neural network, you aggregate the feature vectors of the neighbors, and this leads to something like a diffusion happening over layers. So when you look at the output layer, so here the different rows represent different nodes, and different rows represent the feature representations of different nodes. So all the nodes feature representations converge to a similar value, making it hard to tell apart which class it belongs to. So this is the challenge of oversmoothing. And we test the performance of our model on oversmoothing problem. So the magenta curve, the red curve is our model. So we can see that the red curve the accuracy doesn't drop as you increase the depth. So, and it's very comparable to another model which is specifically designed to solve the oversmoothing problem called the graph neural diffusion. So our model overcomes the oversmoothing problem. The second challenge faced by graph neural networks is that of homophily. So let's consider this graph. It's a homophilic graph. So here the color indicates the class that node belongs to. So in a homophilic graph, all the neighbors of each node belongs to the same class. Every neighbor looks like you. For example, in the heterophilic dataset, every neighbor belongs to a different class. So your neighbors look very different from you. And these are two extremes. So whether a graph is homophilic or heterophilic can be quantified using what's called the homophily ratio, which is basically the fraction of edges that connects nodes of same labels to the total number of edges. So in the case of homophilic, in this case, the homophily ratio would be 0, and the homophily ratio would be 1, and in the heterophilic data set, the homophily ratio would be 0. So the plot here shows the variation of accuracy with homophily ratio. So in a very homophilic graph, so for example, let's consider the graph convolutional network, GCN, the popular GCN. So when it's a very homophilic graph, it attains a good performance. But when the homophily ratio decreases, for heterophilic graphs, the performance is, the accuracy is really low. Whereas in the case of MLP, the accuracy doesn't vary much based on the homophily ratio. It's just constant. So so basically graph neural network architectures have a low accuracy during low homophily ratios. With experiments, we show that our model doesn't suffer from the homophily problem. So for example, the red is our model. So for heterophilic graphs, for low homophily ratios, we have a performance comparable to the MLP, and for the homophilic graphs, our performance is comparable to the blue curve. So comparable to the GCN. So it's basically like offering the best of both worlds. And our performance is very close to the cyan curve, which is another popular model called GREED. And also we can see that GRAND, the other model, suffers from the homophily problem. So yeah, with that, that was all the experiments we had. So now, basically, in summary, we presented two new permutation equivariant symplectic graph neural network architectures arising from the different parameterizations that we use. And then we demonstrated the efficiency on identifying Hamiltonian systems in two different examples. And we also showed the effectiveness in node classification problem. Future directions include extending this to dissipative systems, time-dependent Hamiltonian systems, and systems with non-canonical coordinates. Yeah, that's all.
Great, thank you so much, Alan. Do we have any questions from the audience?
Hello.
Hi.
Hi.
Hello. Can you hear me?
Yeah, I can hear.
Okay. My question is about you built a graph for the particles, right?
Right.
Yes. So I mean, how did you how did you design these connections?
Oh, so in the case of that's a good question. Thank you. In the case of the coupled harmonic oscillator, so we know which particles are connected to which particles based on the springs. So based on those connections, based on the springs, we constructed the adjacency matrix. Whereas in the case of the example of the 2D Leonard zones the particles in the 2D Leonard zone potential, we for each time step we computed the distance between particles, and if the distance is below a threshold, we assume that those two nodes are connected.
Okay. So it's like it's still based on the physical distance of the nodes to design the connections.
Yeah. A similar approach has been done by for example, the DeepMind paper for fluid particle simulation. There also they construct the graph based on the distance between two particles. If it's below a certain threshold, they assume that those two nodes are connected.
Yes. Okay. So that does not change the Hamiltonian so much, right?
Right. Yeah. So these examples were using the graph constructed based on the physical distance, and we see that the energy doesn't vary much with time.
Yes. Okay. Understood. Yeah. Thank you.
Thank you for the question.
Thank you. Do you have any other questions from the audience?
Hi, Alan.
Matthias.
This is PV from UGA.
So actually, I have a question. You mentioned at the beginning the DeepMind cases. So were you able to like kind of using your approach to reproduce those examples of waters in the shaking box and compare if your result is more accurate than their prediction?
Oh, right. Yeah. Thank you for the question. So here we didn't we didn't attempt this problem because so in the fluid particle simulation, it's a dissipative system. And our model is for Hamiltonian systems where there is no energy dissipation. So we didn't try solving dissipative systems. So solving dissipative systems, developing architectures to handle dissipative systems is part of our future work.
Okay. So but what I remember you mentioned the one of the limitation of their simulation is that they cannot do long-term predictions. Right? But the approach you propose seems can do long-term prediction.
Right, yeah. But we right now we can handle only non-dissipative systems. So that is like the SympGNN is specifically for non-dissipative systems. So if we can extend this to handle dissipative systems, then we can try to solve the fluid particle example problem.
Okay, thanks.
Thank you for the question.
Great. We also have a question from Matthias. Matthias, can you hear us? Yeah.
Yeah, thanks. First, thanks a lot for this great talk, Alan.
Thank you.
I'm sorry, I just have a comment. So, since you mentioned you want to extend your approach to dissipative and time-dependent Hamiltonians, I just wanted to propose that there's already an existing framework called port Hamiltonian systems, PHS. And so they are dissipative and time dependent, and moreover, they have these ports which allow some interaction for other systems, other subsystems. So this goes in the direction of multiphysics. So I think it would be a good idea to direct the generalization to this existing framework.
Right. Yeah. So if we can make the port Hamiltonian systems permutation equivariant, then it would be like really useful. Yeah, we can like look into the port Hamiltonian systems and see how we can make it permutation equivariant.
Yeah.
Extend it to graphs, basically.
Yeah, I think you have to develop some loss functions for the ports, for the couplings.
Oh, all right.
Thanks a lot.
Thank you for the suggestion. I think Juan, you're on mute.
Yanq, you have a question?
Yes, I have a question. Hi, Alan. I am
Hi.
Yanq, postdoc in French group. So I'm just curious about the oversmoothing problem. Can you go back to slide?
Yeah.
The oversmoothing.
This one, right?
No, your architecture can overcome. Yeah. So how can it possible to overcome this smoothing? Is there any structure to help to
right. So
overcome the oversmoothing, or is it came from the structure of the SympGNN?
So we just like show the empirical results. So it's just a numerical example that we did. So we don't know why exactly the SympGNN alleviates the oversmoothing problem. So I think one way to look at it would be to look at the eigenvalues of the metrics. But we tried that, but we didn't reach anywhere. So right now, like we don't know why exactly it overcomes the oversmoothing problem, but we empirically demonstrate that it overcomes the oversmoothing problem.
I see. But how about the GSympGNN? There's only array SympGNN in the plot.
Right. So in the node classification examples, we experimented only with the LA SympGNN. So for some initial experiments that we did with the GSympGNN, we didn't get good accuracies. It was behaving almost like an MLP.
Okay, thank you so much.
Great. Do we have any other questions from the audience? It looks like we do not. So I think that with this we can close this week's seminar. Thank you so much, everyone, for your attendance today, and also a special thanks for our speakers. And with this, I think we can close it. Thank you so much, and I hope you have a good weekend.
Thank you.